Hello, Mr. TA who is grading this. Thank you for taking your time out of your busy schedule of grading other people's lab reports to grade mine. This is Matthew Lee. Okay, so this is my code. It's just basic stuff, basically what we did in class, but I did a both rotate instead of a right or a left rotate. So what that means is there's one input for the 32-bit data that we want to rotate, and then we've got an input for how much we want to rotate it left, how much we want to rotate it right, and then an output that is left rotated and an output that is right rotated. So so you can see right here the B number is used by the select function to determine uh, how far left rotated it is. So the select function works by reading the input at, in this case, B, and comparing it against its lists of choices. So if, for instance, it was a 1, then the output would be left rotated 1, and it would set the output O to this A value. Excuse me. And or if it was I don't know whatever this is. I don't remember binary. It would pick this as the output. And then down here is the left rotate, or the right rotate. This was the left rotate. This is the right rotate. The right rotate, which is basically the same thing, except the numbers are backwards. So this was this is the same action as this is, but for the right rotate, it's the opposite number, basically. And it's outputting the P instead of O. So it does both at once. Here is the simulation. You can see I chose a very easy number, so you can tell like the bunch of ones, so you know exactly how far left or right it's gone. So the first thing I did was 10,000, not 10,000, binary, whatever. And this is where the left rotate, which is B and O, and the right rotate, which is C and P, have the same, like they meet in the middle. This is the same as the left rotate and the right rotate are the same for these values. And then I did it for different values, added one on the left rotate and subtracted one on the right rotate, and they're still the same output values for O and P. And then for a different value for A, different values for everything else. Here's two more test cases that I'm sure are great. And then the block diagram is right here. So I chose to use 32 5 to 32 demuxes where the input is B. So basically A is the enable. So this is you know, it's just a mux but backwards. And so the this routes the okay, it doesn't whatever. It works. This chooses an output, and A enables the output. So the B's would choose how far this is rotated, and each of these demuxes would have to be set independently of all the other demuxes. So the demux for the enabler A2 would be different, of course, than the demux for A1, but they're remarkably similar. Um, and so you can see it outputs to M1, which is just, you know, the in-between signal. So M1, 1, for instance, if this was all 0, would then be routed to an AND with all of the possible, with all of the M1, like M1 for the first mux, demux, and all the way up to M31 for the 31st demux would all be, and all of their 1 outputs would all be ANDed, and the output would be O1. And then for the right rotate, it would be the same thing, except for using C over here, N over here, N down here, and P over here. So it would be the C input would choose the output, and the A enabler would enable an output at that pin. So all of the pins that are 1 or all the pins that are 28 would all be routed to 1 and. So for this one, it's all of the pins that are 1s would be routed to 1 and using the AND signal, which is, of course, the in-between signal. And all of those 1 outputs would be ANDed to make the final P and output. And last but not least, the hand calculations for these test results will be on this PDF when I submit it. Thank you for your time. I'm going to go to sleep now. How do I turn off the recording?